Hi, everybody. Welcome. I'm here to introduce Dr. Monika Kress. She is an astrophysicist teaching at San Jose State University. And I originally met her a couple years ago as she was preparing for her trip to Antarctica. So I'm very excited to hear about this talk. And without further ado, here's Monika.
Well, thanks very much for having me speak here. It really is quite fun. I've given this talk before as a public talk for retirement home and for an elementary school and stuff. And what I find is that people are just really psyched about science and stuff like that. And I would hazard a guess that there are an awful lot of people here who were probably dinosaur geeks when they were this big and that kind of thing. Anybody going to fess up to something like that? Okay. I was too, except I never really quite got over it and somehow wound up doing astrophysics and getting into meteorites and that kind of thing. And so before I get too far into this talk, I have to thank all of the people at McMurdo Station, which is the main base down in Antarctica that the United States runs all its missions out of. And if it weren't for these hundreds or thousands of people at McMurdo, washing our dishes and patching up our tents and all that, this mission and all the other ones that go down to Antarctica would never have happened. So definitely a big thanks to all the people down there that don't get to always share in the glory of the science that comes out of that amazing continent. So I'd also like to acknowledge an affiliation I have with the Virtual Planetary Lab, which is one of the NASA Astrobiology Institute teams who also supports my research. All right, okay, so this is what makes me go forwards. Hello. Okay, now what? Okay, here we go. So the trip that I went down there on is called the Antarctic Search for Meteorites, or ANSMET. And it's supported historically by the National Science Foundation, although NASA had been shipping in some money for the last few years. And we all hear about these sample return missions, like the Stardust mission that just brought back samples of a comet, and there's a Japanese mission that's trying to bring back pieces of an asteroid. And but this really is the cheapest sample return mission of all time, except we can't really be that picky about where our bits of pieces of outer space come from. They might come from, most of them come from the asteroid belt, but a lot of them, some of them come from the moon, and even a few come from Mars. So what my mom wanted to know was, well, I understand how meteorites can be interesting and stuff, but why do you have to go to Antarctica? Why don't they fall in New Jersey or something like that? So, but it turns out that Antarctica is one of the best places to look for meteorites because it's a polar desert environment, which means that rocks from space that fall to Earth, these rocks have never seen water and they've never seen oxygen. And those are the two things that eat rocks. And so once these things fall to Earth, they're very susceptible to be weathered, except in Antarctica, they get preserved because there's no liquid water down there. They're not sitting in puddles. And, but also the ice flow and the wind patterns tend to concentrate these meteorites in certain areas, and I'll talk a little bit more about that. And then, of course, it certainly helps that ice is bright white and these rocks are black. That also kind of makes them easy to find. So it all starts in Christchurch, New Zealand, and here we are wearing our extreme cold weather gear in sunny summertime Christchurch, New Zealand. This is December, or the end of November, getting ready to get on the plane. All the flights to McMurdo fly out of Christchurch for the United States missions. So here's some of our team members just baking in these horrifying outfits that we had to wear. And then the luxurious first-class trip down to the ice. And so I have to point out here, you can probably find me in there. I'm the blonde one right there. This is our PI, Ralph Harvey, and a couple of my teammates. And we're basically stuffed in there with all of our gear and everything. And back here, this little sheet here, that's the bathroom. So that was kind of an interesting 8-hour-long flight. And the plane that we flew down on, it takes off with the wheels when we're in Christchurch, and then to land on the ice, down on the, actually on the ice sheet, not even on land. The runway is just basically flattened out ice and snow, and it puts down the skis. So that's also what makes this airplane so slow, too, because it's got this landing gear that's just hanging out of it the whole way. So the LC-130 Hercules is flown by actually the New York Air National Guard. And here's McMurdo, lovely, scenic McMurdo. And here are some of the dorms. This is the ocean coming in here, frozen. This breaks up later in the summer. And over here somewhere, you can't really see it, but there's Robert Falcon Scott's hut at that point. So that's the Discovery hut from which he launched his 1902 mission. And that was really cool. We got a chance to go in there and walk around and look at all the stuff in there. And there's some science labs. Here's the Crary Science Lab, where we spent a lot of time. And over here somewhere is where all of our gear was. And we had to pick up all our tents and everything. All that stuff is already down there waiting for us. And of course, safety is a huge issue down here, not only because of the cold, but because of the hazards regarding crevasses and other things that we might run into. So we had basic mountaineering training, which meant learning how to tie knots, basically, and learning how to get ourselves out of a jam if we ever found ourselves dangling into one of these, which was frowned upon. But what they tried to do was to teach us what to do if we or one of our teammates fell into a crevasse. If we were ever in an area like that, we'd have to be roped up and stuff. So after a couple days of learning how to do stuff they don't teach you in graduate school, such as driving a snowmobile up a 50-degree slope, we did that for a few days. That was fun. I have to say, that was quite fun. We had to pack up our supplies and take a closer look at what some of our supplies were. Not just tents and food and stuff like that, but also we had some goodies there. There's the Bombay Sapphire. Can't go in the field without that. A lot of people ask me about the weather. And anybody ever live back east or like in Florida or something like that? And when they ask you about the weather, it's like, it's not the heat, it's the humidity. Well, in Antarctica, it's not the cold, it's the wind. And it doesn't even matter what the temperature, the air temperature is, but if that wind is blowing, it's a very, very unhappy place to be. And at the South Pole station, this is the weather report for the South Pole, wind blowing at 9 knots, pretty standard. It could blow up to, we had a couple days where we had 30, 40 mile an hour wind. And this past field season, I heard that they were having gusts up to 50 miles an hour or even more than that. So it was pretty wicked. But the air temperature, this is pretty standard, I guess, somewhere a little below 0. That's pretty typical for the places that we were. Okay, let's talk a little bit more about the science part here. So meteorites can actually get preserved in the ice for thousands of years, and in some cases they've found meteorites that were actually entombed in the ice for millions of years. I think that the oldest was 2 million years residence time on the Earth. And so we're not looking for meteorites that fell yesterday, because remember, only one meteorite per square kilometer per 10,000 years falls, meteorite that you can actually see. There's lots of little micrometeorites falling all the time. So the average time on Earth, or what we call the terrestrial age of the meteorite, is somewhere between 25 and 65,000 years. That's where the ages cluster. That's also, that 25,000 year figure is also the amount of time roughly since the end of the last ice age. So since then, the ice sheets have been shrinking away, and as they do so, the meteorites that they were holding get stranded on the surface. Most meteorites that we have in our collections here on the Earth are 4.5 billion years old. They slightly exceed the age of the Earth, and they're essentially the same age as the Sun. And so when we find a meteorite that's younger than that, then that's what's really exciting, because that means it's not just yet another piece of the rubble left over from the formation of the solar system. Although that stuff is great, it makes up most of the meteorites that are falling. So I haven't worked back my, my vocal cord calluses since I started teaching yesterday, so this might be a little bit scratchy. But the meteorites that fell over a large area actually get concentrated by not only the ice sheets shrinking or deflating, but also the motion of the ice, and there are certain areas that the ice flow actually kind of stagnates as it's flowing through the Transantarctic mountains eventually to the sea. So back in the day, the Antarctic continent was explored by a number of methods, some more successful than others. And here I'm showing some images from Robert Falcon Scott's trip and Shackleton's trip to the continent. And the preferred method by the English, at least, was man-hauling stuff, and they also tried ponies. The ponies worked out better as food than they did as anything else. And the Norwegians, of course, used skis and dogs, and it was a slightly more successful way. We used snowmobiles, and those work just fine. They're a little rough on the ice because we're not driving on nice, soft, fluffy snow. We're driving on solid ice most of the time. But our tents, these yellow tents here, they are essentially the same design as the tents that were used by the Scott and Shackleton expeditions. Basically 9-foot by 9-foot square, double-walled canvas, pretty windproof, not completely windproof, but close to it. And they actually were pretty good, as home sweet home for the 7 weeks that we spent in the field. We also have a solar panel so we can charge up our computer. We've got a radio. This is the radio tower, so we could at least talk to McMurdo. We also had a sat phone so that everybody could talk to their wives and girlfriends and boyfriends and whatnot back home. And so here's the plane again. And so this is how we loaded it up when we were getting out of the field. Just kind of loaded up our sleds and drove them into the plane. But in case you were ever wondering how to put a snowmobile in a small aircraft, you just basically drive it in. It's the only way to do anything with these guys. I was on a reconnaissance team, so we actually changed locations about once a week. So we'd have to rip down camp, pack everything up, shove everything in these little airplanes, and then get schlepped on to our next search location. And so it took us 4 flights to relocate the 4 team members to our new site. And on each flight, we'd have a person, a snowmobile, an oil drum, or a fuel drum, and a tent and supplies and stuff. By the way, if you ever go to Antarctica, don't bother bringing Cliff Bars because they turn to the consistency of like a hockey puck and they're completely inedible unless they've been sitting in your armpit for about 3 hours. And it's very uncomfortable having a frozen Cliff Bar in your armpit for 3 hours. So here's the Antarctic continent, and the continent is bisected by this range of mountains called the Transantarctics. And they're largely volcanic in origin, so they basically were formed as, I don't know what the official geological term is, but this huge amount of volcanism came in and basically built this huge rift made out of basalt, which is a very heavy volcanic igneous rock. And so most of the Transantarctics, at least where we were, was made out of this very dense, kind of dark reddish type of rock. And it's very interesting geology, and also all the geology is just laid bare for you to see. There's no vegetation covering this or anything. Really fascinating. We found fossils tumbling out, not in the basalt, but there's sedimentary rock down there too. We found fossilized wood. We found fossilized sea creatures and stuff like that. Really interesting place for geology. And what's going on is that, so the South Pole is in here somewhere, and snow falls all the time. It's actually very little precipitation. It's officially a desert, one of the driest deserts in the world. But the snow piles up and eventually gets compressed to ice, and all that ice is gradually flowing to lower elevation, meaning towards the sea. And along the mountains here, the ice has to get through the mountain passes, and these glaciers carry the ice to the sea. But in certain locations, the ice flow stagnates, and it makes that ice vulnerable to ablation by these katabatic winds, which are gravity-driven winds that blow pretty much continuously all the time. They're just, the wind direction and speed is relatively constant throughout the field season. And in these regions that are continuously exposed, I'll skip that for a sec. These regions that are continuously exposed to the katabatics eventually all the snow gets blown away. Whatever piddly little snowfall, like 1/2 millimeter of snow which might fall, gets blown away immediately. So you're walking around actually on snow that was compressed to ice 25, or 45,000 years ago. And that was our drinking water too. It was pretty good water, I have to say. And so the ice flow is relentlessly heading downhill, and in these areas where the ice flow gets kind of halted, that's where we find the meteorites. So these blue ice areas. And the reason that the ice is blue, and it really is blue, that's a close-up of the ice. And in fact, I think my camera didn't quite get the real impression of this. It's this amazing translucent, just 3-dimensional blue. It's because that's what color ice really is. The reason that our ice cubes are white is that we're not looking through enough of it, and also there's a lot of air bubbles and stuff in our ice cubes in the fridge. But if they were compressed and you were looking through 100 feet of it, that's what color it would be. This is taken from a higher elevation airplane, so I got this from the U.S. Geological Survey. But you can kind of see that we've got an ice flow. This looks like it's sort of oozing, and there's even like ripples, and over here too. this really is ice. All the dark gray stuff is ice, and the white stuff is snow. So the snow gets blown away, and the ice flow and the wind sort of conspire to make certain regions very rich in meteorites. Here's just an average day cruising around, driving these snowmobiles across the ice. So it's just this loud, I mean, it looks like this beautiful, serene picture, but let me tell you, you got this two-stroke engine rattling across ice. It's like, it's awful, but it was actually a huge amount of fun. And we would just drive, the four of us, across in a row, and when you saw a rock, you'd drive up to it, stop, get off, look at it. If it was a meteorite, we'd wave, have everybody come over, and they'd laugh at you if it wasn't a meteorite, and if it was, we'd collect it and put it in a bag and stick it in the box. And so I'm showing this. This is the most blatant example of a meteorite. This is actually rather large. Most of the ones we found are probably smaller than a golf ball, somewhere between golf ball and Hershey Kiss size. The meteorite size range that we find is basically determined by the resolution of human vision at a certain distance away. So you could probably see a Hershey's Kiss on this bright white ice from a distance of at least 50 meters. But this one is so obviously a meteorite. I'm sure you've never seen a rock like this. If you have, please let me know. It's all burnt and kind of cracked on the outside here, and it's all smoothed off too. And this is in a region where the rocks that crumble out of the cliff just look like somebody chiseled them out with a hammer. They got all these jagged edges on them and stuff. But this thing, all the edges are burnt off. They're all smoothed off, and this thin crust, which kind of looks like something I would have cooked for dinner or something. This burnt crust has chipped off to reveal something different underneath. So that was basically our standard type of rock that we found out there, or type of meteorite that we found. And so here's what happens when we find one. We want to pick it up and collect it with as sterile conditions as possible. So yeah, okay, it's been laying around out in Antarctica for a while, but there's hardly any organic matter and almost no detectable bacteria out there in the ice. It's all they can do to kind of scavenge a few bacteria that probably blew in from somewhere. So we just got to make sure that we don't see this crack right here. It's actually a crevasse, and that snow that you see on there is probably just a few inches thick, and so we had to make sure not to step on those things because you could really twist your ankle. The big ones, you could see the big ones, so it wasn't, those were easy to avoid. You're not supposed to touch it, but you're also supposed to make sure it's a meteorite. Sometimes these two things are mutually exclusive of each other because you'd stop and if you're not seeing any meteorites for hours, and you'd stop and be like, stupid rock, and pick it up, and it's got fusion crust on the other side, and you go, oh, oops, and put it down, and here's one. So then we take a GPS position. All of these are recorded, and we stick a little flag in there where we found it. It gets a field number and a photograph, or 2 or 3. We take the dimensions just roughly, just 2 inches by 3 inches by 5 inches or whatever, and then make some just superficial comments about it. Is it 50% covered by fusion crust, 90%, 100%, whatever? And then it goes in a sterile sample bag, and the next time it will see the light of day is in Houston. And in Houston, there's the Materials Curatorial Facility at Johnson Space Center. And so they're going to thaw these things out under dry nitrogen and then put them in storage and send half of the meteorite samples to the Smithsonian Institution in Washington, D.C. So that's the procedure there. And here's what happens when you step on one of those little crevasses. So that's just a close-up of my footprint, which was like 50 feet deep. This is one of the bigger crevasses, so if there were any interesting looking rocks on here that we wanted to investigate, they just got left there. So all of this is a very thin layer of snow that covers, like what we were just looking at here, except more like 10 feet wide, so you just couldn't drive on that. Any snow was suspicious, especially the stuff that had that kind of frothy, whipped appearance to it. So I developed this unnatural fear of Cool Whip while I was down there as well. And this was a cool shot. This is the Antarctic Ice Sheet where it meets the Transantarctic mountains, and we can see that the ice sheet, it's not grinding right up against the mountains, but from my take on this, it looks like the mountain is actually almost heating the ice sheet and causing a lot of evaporation and ablation along this leading edge. Just to give you an idea of the height here, this is one of my teammates standing there. So this thing is, I don't know, like 30 feet high or so. And we also had to be very careful in areas like this because we didn't want to do any backwards downhill snowmobiling, which I've tried a couple of times. Can't say I recommend it, because you don't know what you're going to wind up at the bottom of. Here's another meteorite. This is a carbonaceous chondrite. This is in the category of meteorites that are common. The chondrites are the most common, but among those, only about 10% are of these carbonaceous types. And the carbonaceous ones, they're much more friable. They sometimes can have the consistency of, dried clay or something. And the reason they're so interesting to my field of research, which is like origin of life and origin of the Earth, that kind of stuff, is that these meteorites are known to contain amino acids and nucleic acid bases and stuff like that. And that's just really interesting to try to investigate, when people are thinking about the origin of life, what kind of materials were actually falling on the Earth. We assume that meteorites haven't really been changing composition all these billions of years. So those are very interesting types of meteorites to study. Here's just a cool looking one. The chemistry of the meteorite itself is pretty standard. It's an ordinary chondrite, so it's not as rich in carbon as the other one. But this particular meteorite had a preferred orientation when it came through the atmosphere. Usually when meteorites come in, they're tumbling around and they get burned on all sides, nothing preferentially. But this one took on the shape of a nose cone of a rocket because it already kind of was that shape when it hit the atmosphere. And you can even see here, there's like these streaky patterns. That's from when that outer shell or the outer layer of the meteorite gets so hot that it melts away. And when it melts, it leaves this streaky pattern like that. So that was a cool one. Got a couple other cool ones here. Some things kind of gave us pause. This one we found just laying around out there. There was nothing else out there. And we picked it up, and it didn't look particularly like a meteorite. It's not black. It doesn't have fusion crust, but there was nothing else out there. This one also, this we found on day 3, and it looked totally different than these, than that kind of reddish, kind of hamburger-y looking texture of the ordinary chondrites. So when we found this, we knew it must be a meteorite because there was nothing else out there, and it had kind of this very glassy black fusion crust on it. So rocks don't just burn, especially when they're laying around in Antarctica. So we picked that one up, and oops. So I missed my little joke here. It was like, how do we tell if they're from Mars? Which is, they come conveniently wrapped in a wrapper. But actually, this one that I just showed you, this one we found out like in July after I got back, that this one actually was a meteorite from Mars. We knew at the time it was something special because it didn't look anything like any of the other meteorites that we found. It was all real dark black and sparkly and just totally different from all the other meteorites. And we knew for sure it was something special, and it turns out that, in fact, it was the first Martian meteorite that had been found in Antarctica for the past 9 years. And it was the first of Martian meteorites called a knocklite that was found in Antarctica ever. So that was a huge, huge discovery for us. And so it takes its place as one of the 30 known Martian meteorites that we have in our collections here on the Earth today. Surely more of them laying around out there. Here's another kind of weird-looking meteorite. This one definitely is a meteorite. It's got this black, kind of shiny fusion crust on it, but the inside looks totally different than some of the others. So this is, who knows what that one is. It could be from an object, or it definitely is from an object that is differentiated. And by differentiated, what I mean is that it got big enough to melt so that all the iron fell to, sank to the center of the object, leaving the lighter, stony stuff on the outside. And so this is a stony meteorite. It doesn't have any of those little chondrules, these little, they're like little glassy beads about the size of BB shot, or a little bit bigger than that. That's the hallmark characteristic of the chondrites. So when we see something that does not have chondrules, and we say, oh, okay, this is something different, this is something particularly interesting. Here's another achondrite, so something without chondrules. Just cool looking thing, and it's white, who knows why. Okay. In this particular location, we actually found not just a few unrelated meteorites, but we found 80-something fragments of the same thing. So this original object came in and shattered into a zillion pieces, and we found something like 84 of the larger fragments in this particular location. And here's where our flags are. I don't know if you can see, but there's a flag here, 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 all along here. It looked like a golf course, actually. And one of the challenges about identifying meteorites is that sometimes they don't really look like anything special. And so what I did here was put a meteorite next to just your average rock that we were finding in the Transantarctics. So one of these is that classic red basalt that is typical of the Transantarctic mountains, and the other is a rock from outer space. And so in case you're wondering, this is the meteorite, and this is the chunk of basalt, but they were infuriatingly similar looking. So these are some of the meteorites that we found in the Otway Massif area, that strewn field that I was talking about. One of the reasons that we had a hard time identifying the meteorites at first is that they were all, they defied our usual picture of these things that have been all burnt and had all the jagged edges burnt off of them. These things were nothing but rocks with jagged edges hanging off of it, which indicated that it broke up at a very low altitude and relatively low speed and didn't get all of their rough edges burnt off. That was the biggest fragment of the Otway Massif meteorites that we found. That thing weighed about probably 60 pounds, and it only has a little tiny piece of fusion crust on it, and the rest of it's just a busted up rock. And there's Gretchen Benedicts and I, my tent mate and I, sitting next to that big fragment. Okay, so here's an interesting area. We were at this place, I think this is called Roberts Massif, and there were no rocks out here. We drove around for hours and hours and hours. And then we came across this spot where every little rock that had been scattered along out here got dumped right here. Like everything, whatever tumbled out of the cliff, whatever meteorites there were, anything got put there for whatever little conspiracy of physics. We spent hours going through this little aeolian deposit of rocks. And so if we take a close-up of some of these rocks next to each other, you can imagine, in fact, I'm having a hard time looking at this now, wondering what's the meteorite and what's the meteor wrong. My guess is the one that has not been disturbed is the one that's the meteorite. And when we find something just laying around out in the middle of nowhere, like, who knows? That was just a regular rock, but there was nothing else out there. So it was really kind of strange. Oh, here's a close-up of that little patch of rocks that I just showed. Anybody want to guess as to which object in here is the meteorite? I think the first thing that jumps out is the pocket knife. So the first thing you notice is that something's not like the others. There we go. Who's got the laser pointer right here? Yeah, so this little shiny burnt thing, and once you see it, it's like, oh, duh, yeah, how could you miss that? And really, that's what it was all about. There was no scientific training. I mean, I have a PhD in astrophysics that was absolutely worthless for this trip, as far as I could tell. And so it was basically just look for rocks that look strange. And here's another Where's Waldo picture. There are actually two meteorites in this picture. One thing that always jumps out at me is this weird white thing. It's like, oh, there's this white rock in the picture, but there are actually two meteorites in this picture. Anybody else with a laser pointer? Okay, so we got this kind of burnt, shiny thing here. No? They're actually sitting right next to each other. You know, there we are, this giant pile of rocks, you know, like 50 feet long and 10 feet wide, and the two meteorites were sitting next to each other. This is actually interesting because it was one of those carbonaceous chondrites. And I think, from what I recall, it was also oriented, so it was kind of fried on one side and not on the other. But they're all about the same size, roughly. Okay, so the last couple of shots are just the gratuitous pretty picture shots from Antarctica. This is our camp manager and team leader, John Scott. He's been doing the ANSMET trip for the past 25 years, pretty much since it was invented back in the late 70s. And so he's a very hardened Antarctic type of person, and also an excellent geologist, field geologist. So he's standing here, and in the background we have one of these glaciers just with a blind end to it. If you've ever been up in the mountains here, all of our glaciers up in the mountains and stuff have a river running off the end of it. Here, the ice just crumbles away and evaporates. There's no puddle. It's too cold for any liquid water to persist for long. And we could see evidence that at one time, this entire bowl-shaped valley that this glacier looked like it was flowing into, we could see these bathtub rings, these lateral moraines and terminal moraines up on the edges of the cliff that, you know, told us about this history of the deflation of the ice sheets for the past, 20 to 30,000 years. I don't know if this came out. Oh, yeah, it kind of did. Antarctica is famous for having really amazing solar halo displays. And on the morning of what actually was the 41st birthday of one of my tent mates, or one of my teammates, we woke up in the morning to this incredible solar halo display. So we had the 22-degree halo. We've also got sundogs. They're also called parhelia. And the parhelic circle, which kind of goes straight through like this. And then also we had an upper tangent arc and a whole bunch of other arcs and these other things. And it just took up the entire sky. Your entire field of view was just rainbows are everywhere, little weird-shaped rainbows. It was just one of the most incredible things I've ever seen. And so just to wrap up, it's kind of hard to summarize everything into one little blurb, but my favorite quote is from Dr. Seuss: "If you want to catch beasts you don't see every day, you have to go to places quite out of the way. You have to go places no others can get to. You have to get cold and you have to get wet too." And I just also want to thank a couple of different entities up in the Seattle area, which is where I lived before I came back down here to the Bay Area. So the Juan de Fuca Festival of the Arts, Evergreen Elementary, Al McPhee, who is the patron saint of meteoritics as far as I can tell, and Horizon House. And they all have made donations that enabled me to buy some meteorites off the internet. I don't have any Antarctic ones, but I do have ones from eBay and various other sources. So if you'd like to come up and take a look at these afterwards, you're more than welcome to. So, well, thank you very much. Questions? Yeah.
So how do you know they're from Mars?
How do we know they're from Mars? Okay. I'm glad you asked that because I meant to talk about that. Well, when we're out in the field, we don't know. All we have is our eyes, our hands, and sterile sample bags to put these things in. But so at first glance, you just kind of know that it's not a chondrite. You know that it's not one of the usual types. Once it gets back in the lab, what they do is to compare it to the other Martian meteorites. So mineralogically, they took one look at it under a microscope and said, that's a noclite. The way the first Martian meteorite was confirmed was that somebody extracted gases from these little bubbles within the rocks. And when they analyzed those gases, they found that those gases had the exact same composition as the gases in Mars's atmosphere that were determined by the Viking missions. And so the joke was, okay, well, if it doesn't come from Mars, then it comes from some other planet that looks exactly like Mars and has exactly the same type of atmospheric chemistry as Mars has. So the simpler explanation being that it's from Mars. But they were originally misclassified as differentiated asteroidal meteorites initially. Yeah.
So how does a rock just take up the surface of Mars and travel to Earth?
How do they get knocked off the surface? Well, what happens is that every few tens of millions of years or so, or just millions of years, a planet can suffer an impact large enough that it will make a pretty decent-sized crater. And Mars has only 1/10 of the mass of the Earth, so it has much lower gravity from Earth, and it also has only 1/1000th of the atmosphere. So it's easier to get away from Mars. If Mars gets hit, those rocks can escape, because there's less drag and less gravity to escape from. It's harder to launch rocks off the Earth and near impossible to launch rocks off of Venus in this way. But people have actually done calculations where they slammed Mars with something, not unreasonable size and not unreasonable speed, and figure out the trajectories. So the history of these Mars meteorites is that there's a collision probably, tens of millions of years ago, and the rocks go everywhere. Some of them fall back on the planet, some of them leave the solar system, some of them take them on trajectories that will eventually lead them to Earth. And I think the number is something like these things will be out in space for, I can't remember the exact number, but something like on the order of millions of years and then land on the Earth. The ones that do get here take about that long. Yeah?
How do you date the time on Earth?
What?
How do you date the time on Earth?
Oh, this is good. When the rock is out in space, it's being irradiated by cosmic rays, which we're shielded from down here on the Earth. And when the thing is out in space, it's getting bombarded by these cosmic rays, which actually create new nuclei in some cases. So through nuclear reactions, you get elements, I think beryllium is one of them, different isotopes of relatively short-lived elements that undergo radioactive decay, and so they kind of reach an equilibrium value when they're out there in space. Once the rock gets to the Earth, now they have no more production rate, and they're just tapering off over time. So they look for those elements that are produced by cosmic rays out in space, and then they see how little of that is left here on the Earth, and they can actually get a terrestrial age for the rock on the Earth. Yeah, back here.
Find out from analyzing these meteorites now.
Well, the Martian ones, that's like a free trip to Mars, except you don't know exactly where on the surface it came from. And one of the things that we're very interested in regarding Mars is the history of water on Mars. And how long did liquid water persist? We know it must have been there, but was it a few hundred years? Was it hundreds of thousands of years? Or did Mars have a warm, wet climate for a billion years? And what we're hoping these rocks can tell us is, at least for the time that the rock, so some of the noclites are only about 1 billion years old, maybe 1.3 billion or so. And that can tell us what was going on Mars in that time. Were these rocks ever exposed to liquid water? So that can tell us, did that rock see a liquid water environment 1 billion years ago on Mars? So those are the kind of things as far as the Martian meteorites go. For the ordinary chondrites, those are relics left over from the formation of our solar system. So they're telling us about what the building materials for the Earth and the other inner planets was, and what kind of compounds were falling on the Earth during the time that life originated on the Earth. Yeah?
Well, if you can identify rocks on the Mars, can you identify rocks on the Moon if they are like in progress?
Oh, yeah. In fact, lunar meteorites, the first meteorite that was recognized as a lunar meteorite was one of the ones found by ANSMET back in 1979. And so it turns out that there were actually meteorites in our collections, not the ANSMET collection, but people had rocks that they knew were meteorites, but they didn't know where they came from, and they turned out to be lunar after the fact. So the way that you recognize a lunar rock is that we've already got rocks from the Moon because we went there and picked them up. So that was the easy thing. It's like, oh, this looks exactly like that. But we don't have that from Mars. And so that was a slightly more roundabout way to find out the Martian identity. Yes?
So how long were you there for, and how many years?
Oh, good question. I was in the field for 7 weeks, living in a tent, and all the attendant things of living in a tent for that long. And our reconnaissance team found 505 meteorites during those 7 weeks. And there was another team of 8 people down there. Basically, more people means more eyes, means more meteorites. And the 8-person team found 800 and something, like 850, I think. And so altogether, between the 12 of us being down there, we found over 1,300 meteorites, which was one of the biggest hauls of ANSMET, among the bigger. This year, they had extremely bad weather. I was following their web log, and there was some seriously bad weather, including snowfall, which did not get blown away. So they found fewer meteorites, but they still found a lot, and some potentially interesting ones as well. And what was the other question? That was it, okay.
How did it keep warm?
How did I keep warm? I ate like a huge amount of chocolate while I was there. There wasn't really a lot of time to actually be moving around a lot. I mean, we'd move around when we chipped holes in the ice to plant our little flags, but so sometimes just standing there jumping around, drinking lots of warm liquids, and you're wearing just a huge amount of clothing, and then the battery-operated socks. I had a pair of those, which I used sparingly because they go through D cells like crazy. But the boots, I have to say, the boots that the clothing distribution center gave to us, there are these standard Army issue polar exploration boots, or bunny boots, as anybody that's been to Antarctica would recognize bunny boots, and they're horrible. They don't keep your feet warm. They were awful, and so I had pretty bad circulation in my feet for months afterwards. So, and this is going to be broadcast on the web, so do something about that. People down in Christchurch, get us some decent boots, please. But yeah, just eating a huge amount of calories. I'm kind of a snack hound, and I could barely keep up. It was like eating was almost like a chore. Just getting enough calories in. So, yeah.
What's the largest meteorite you
The largest one was probably about that big around, and it weighed about probably close to 70 pounds. And it was an ordinary chondrite, so kind of garden variety meteorite. And it was part of a strewn field that we found like over 80 fragments of it, and hundreds of pounds worth of the same thing. So the people down in Johnson are probably looking at this going, thanks. Yeah, at least it could have been something interesting. So, anyway. Well, if there's no more questions, I invite everybody to come up and take a look at these lovely rocks that I have. And I also have a couple of little tiny ones too. Like these are the show and tell, pass them around types, but feel free to come on up and take a look. Thanks again.